Deuxième qui sera venu dans le cérémoniel Riwa, j'invite pour présenter le professeur.
First of all, I should thank everyone for participating in the event, and also for the delay made by the conference for the logistics issue. So we're going straight to the first keynote presentation titled From Data, Chaos to Visualization, Cosmos, presented by Professor Robert Laramie from the Swansea University, Wales in the United Kingdom. So we'll try to have 40 minutes in the presentation and later 10 minutes or 15 minutes for questions. So we can start.
Happy Wednesday, everyone. I'd like to thank the conference organizers for inviting me here. This is my first time in Morocco, so it's very exciting for me. So today's talk is going to be a little bit unusual, and the reason is because I don't know how it's going to end. So the traditional talk, as we'll see during this conference, is a linear set of slides from start to finish. But this talk is not going to follow that traditional style. I'm going to give, say, a few slides, maybe 3 slides in the beginning with an introduction. And then we're going to have a kind of a special slide. And it has 7 directions, so the talk can go in 7 different directions from that point on. So I'm going to actually ask the audience to decide which direction talk should go in after the introduction. So is everybody going to help me with that? Yeah? Yeah. Okay, good. So it's called From Data Chaos to the Visualization Cosmos, and we'll find out what that means, hopefully, today. So a little bit of history. Maybe it's more fun now that we're in Morocco than somewhere in Europe, but in the 18th century, a lot of historians believe that Europe went through this period called the Age of Enlightenment. Has anybody heard of the Age of Enlightenment? So the Age of Enlightenment was a shift in the way that the collective thought of society is, a shift in the way people think as a society. So it was characterized by things like separation of church and state, or the advancements of science. So science was thought to be more and more important. The relevance of science became more and more important. Personal freedom became more important, and so on. Now, that was the 18th century. In the 21st century, we're going through another shift in the way we think collectively. And we call it the age of digital enlightenment, rather than the age of enlightenment or the age of analog enlightenment. And it looks like this. The age of enlightenment doesn't have a diagram, but the age of digital enlightenment has a nice diagram. So the age of the digital enlightenment looks like this process. So it starts with a real world challenge. This is something we're all very familiar with. Maybe we're trying to build something like a plane. Maybe we're trying to understand a phenomenon. Maybe we're trying to observe something. Maybe we're trying to find out how to improve our teaching or our presentation skills. So it starts with a real world challenge or a problem or a goal. Right? And that's something we're all very familiar with. It's something we all know about. And these challenges, these real world challenges, all have some sort of physical or analog approach. Right? For example, if we want to build a car, we can collect our raw materials, shape them and put them together. Or if we want to observe, for example, marine wildlife, we could actually go underneath the water and try to follow some animal, for example. For all of our real world challenges, our problems, our goals, there's a physical or analog approach. And sometimes in the real world, our challenges or problems, the solutions are not feasible. So if I ask you to build a car, it is possible, right? You know it is possible because we all drive cars. But if I ask you to build one, you'd say, no, that's not feasible, right? Because it's too expensive. So a lot of our real world problems and our real world challenges, even though they have physical solutions in the analog world, the solutions are not always feasible, or they're not always affordable or practical. So we jump from the physical or the real world, sometimes called the analog world, over to the digital world. Right? That's what this dashed line means, the transition from the physical or the real world to the digital world. So whenever we have a problem or a challenge or a goal, we also know that there's a digital solution. Right? We can build software that helps us. Right? For the example I gave with the cars, there's CAD software, right? Or CFD simulation software. We can build a virtual car, right, which is affordable. It's more practical before we build the real world car. And the reason is to save money. Right? And that's true about all of our real world problems and our real world challenges and goals. There's always a digital solution to help us. And these first 4 stages of the age of the digital enlightenment are all things we're very familiar with. Everybody in this room knows about these things, right? We all have real world challenges. We all have goals. We all know that there's a physical solution to those challenges. We all know that we can't afford a lot of those solutions and goals. So we turn to software solutions to help us. We know we can build software, right? We know we can use software. Everybody's trying to develop an app on their mobile phones now to solve all of our problems, right? But the digital world brings new challenges, right? If we look to the digital world to solve all our problems, we face the next challenge, and that's called data chaos. So all of our apps on our phones and all of the tools we use on our laptops and all of the computing power we use to solve our problems cause another problem, a digital problem, and that's something we call data chaos. So this is something we're all familiar with too, is data chaos. Right? We all know that we're collecting massive amounts of complicated, time-dependent data, and we're investing lots and lots of money into that process. Now, the visualization cosmos, so this is where we are right now. We're in this, collectively, we're in this sort of stage, what I would call data chaos. We're struggling to manage massive amounts of time-dependent complex data everywhere we look, right? This is the next step in the evolution of knowledge, or the final phase, or the next phase in the age of digital enlightenment, is how do we get out of this data chaos, and instead of just collecting data, which is not the final, this is not actually what we want to do. We don't want to just sit around and collect data. We want to extract new information, new knowledge, and hopefully wisdom in the end. Right? But how do we do that? So my claim is that we use data visualization as the means by which to come out of this data chaos and into the visualization cosmos. So for anybody that's not familiar with data visualization uses computer graphics to generate pictures of the data, to increase our understanding of the data, right? And we're all generating lots of big data, right? It doesn't really matter where you look, where you turn, right? We can look at the healthcare industry. I don't know what the healthcare industry, do we have public healthcare in Morocco, or is it privatized healthcare? Public and private. I can guarantee you they're collecting lots of data about you, right? It doesn't matter if we're looking at in physicists. Physicists collect lots of data, as I'm sure you're all aware of. Computational biologists collect lots of data, right? About molecular dynamics. Marine biologists collect lots of data about animal movements. Call centers collect lots of data every time you make a phone call, right? That data is collected. Automotive engineers collect lots of CFD simulation data. Sports scientists collect lots of data. Banks, every time you withdraw money or do something with money, that financial transaction is stored in a database somewhere, right? It doesn't really matter where you look. Everybody's collecting lots of data, but that doesn't necessarily mean they're collecting all the information and knowledge that they're interested in, right? Every time you visit a website, right, that data is collected by somebody, at least two parties, right? Every time you move, right, every time you drive your car, that data is collected. Every time you take a train or a plane or whatever, right? Smart city data is being collected as quickly as possible to make the most efficient use of resources. And you also personally like to collect data, right? You collect photos on your phone, selfies, for example, videos and files, right? So this is everywhere and everyone. And part of the reason is just that people like to collect. This is, I don't know why this is, but people generally just like to collect. I think it's some sort of a survival mechanism. We think that we're going to survive better somehow, live longer. We just collect stuff, right? Maybe. So data visualization uses or exploits computer graphics, right? So we, instead of looking at raw data, the basic premise is that if you can't see your data, it's not very useful. Right, so we're going to use computer graphics to show pictures of the data. Maybe they're moving pictures, maybe not, maybe they're static. We're going to see some examples of that. So what is visualization good for? So visualization is good for exploration, data exploration. This is the case where maybe you don't know what your data is. You're not an expert and you're trying to find out what the data is, if it has any patterns, trends, or outliers, or no previous knowledge about the data. Data visualization is also good for analysis. And this is for the expert user who has a hypothesis and wants to confirm or refute their hypothesis using visualization. Visualization is what we usually think of is good for presentations. So after we've done our exploration and analysis, we want to show that or communicate that analysis and exploration to a wider audience, right? Which is what we're going to do today. And it's good for acceleration. So we might be able to see things using visualization in just a few seconds rather than never, for example, or taking lots and many hours, weeks or months searching manually for something. So these are 7 examples of the digital enlightenment here. This is where we have to make a decision about where to go next, right? So we have an example from physics using something called foam visualization. I don't imagine that there are many people studying foam in the audience. We have an example from geography, analyzing and exploring healthcare data in the United Kingdom, public healthcare data. We have an example from computational biology. So in this case, we're trying to understand molecular dynamics and molecular dynamics simulation data. We have an example from marine biology. In this case, we're actually trying to understand the behavior of deep water wildlife. We have a very different example from the previous ones, understanding call centers and their customers, how to use visualization to understand the behavior inside of a call center with, say, millions of calls. We have an example from the automotive industry where we try to understand the way that fluid flow passes through the motor of an engine. And we have a very different example again for sports scientists. So anybody that's trying to understand how to best beat their opponent in some field sport. I don't suppose anybody's heard of rugby. This one's from rugby. Is rugby played in Morocco at all? Probably not. It is? Okay, that's good. Okay, so this is the part that I don't know where we're going to go. So does anybody have a preference for which example? We're not going to be able to look at all the examples. We're going to be able to look at maybe 2 or 3, and then we're going to be done. So you have a. Which one? The automotive engine example. Okay, that's a good one.
We'll have to see how many people compare which one, and then.
Should we take a vote?
Like 6, and then we'll see how many people choose first or second.
So you think we should take a vote?
Yes.
Okay, so who votes for the physics one? Raise your hand if you vote for the physics one. Not that many physicists in the audience. The geography and healthcare? Okay, a little bit more for that one. The computational biology and molecular dynamics? Ooh, that was close. I think the geography is the biggest so far. Marine biology and animal tracking? No animal lovers? I thought. Okay, that one definitely didn't win. How about understanding call centers and their customers? Everybody, okay, that one wins. So, engineering and automotive design, how to drive better. We're not going to talk about driving better, by the way. And then the sports science visualization. Okay, so it looked like the call center won the first one, and then the geography looked like. Yes. Okay. So we'll look at the call centers as the first example then. So these are all examples of digital enlightenment, by the way, using data visualization just as a refresher. So what is happening in this example? Has anybody here ever called a call center before? It's very, actually I know everybody has, and you don't have to ask. You don't have a choice in some ways. So the goal here is to understand call center behavior better, right? Probably you're aware that call centers employ huge numbers of people, millions and millions of people. Right? In the UK, they employ something like 3 to 4% of the entire adult population. So it's really a huge number. In Europe, there are several million people working at call centers. But call centers, we've all had frustrating experiences with call centers before, right? Right? Sometimes we just call the call center and we get frustrated, we just hang up. So it would be nice, if we're managing a call center, it would be nice if we could avoid that and provide the best experience, the most efficient path between the customer and the service they need. So the question is, can we achieve that goal? And how do we achieve it given these massive call centers with thousands of employees, hundreds of thousands of calls every day? There is an analog solution to that, right? The analog solution is just to hire more people at the call center. Hire lots and lots of people, and people whose job it is just to study the behavior inside the call center, find out what's happening, and maybe they stand there with their notebooks and make little notes and observe all the phone calls. It is possible, but it would cost a lot of money, and who knows if it would succeed. And there's also a digital solution. And we work with a company called QPC. That's a little company based in the UK. And what they do is they decided, oh, there must be a digital solution to this problem. We're going to write database software that records every single event in a call center. So every time you call up, right, it's being recorded, all the events, right? Which phone number made the call, which numbers you chose on your phone to get to the menu or the interactive voice recognition system, how long you waited in a queue for, which agent you spoke to, how long you talked to that agent, and so on. And all of these are recorded in an events database. So we have this database with millions and millions and millions of events in it. And how do you make sense of that data chaos? So that's what QPC asked us, if we could make sense of the data chaos. So let's look at a demo instead of slides, only slides. So this is what the software looks like in action, so to speak. And we based our solution on something called, a visualization called a tree map. Has anybody here ever heard of a tree map before? Okay, so let's see what that looks like and see if I can explain it in some way that everybody can understand. So I'll just hit pause for a second. So a tree map is a space-filling visualization. It tries to use all the screen space to depict the data. Each box is 1 hour in a day. So there are 24 hours in the day, right? So we're starting at midnight, and then we end at midnight from left to right. And here we're depicting each event in the series of phone calls. The size of the square in the middle represents the volume of calls in that hour, right? So this is when the call center is closed, these first 6 hours or 7 hours. People do still try to call when the call center is closed, and now we see the volume increasing as the number of calls to the call center increases. So the size of the box is mapped to the volume of calls that the call center gets in that hour. Right, so that's a tree map. This is a tree map visualization, it's called. And we can see right away that everybody tries to call, well, the most people try to call at lunchtime, right? This is when people try to call the call center. And there are also colors being used there. So in this case, green maps is a successful call, and red indicates an unsuccessful call. An unsuccessful call is when the person just hangs up and is out of frustration with their call center. Right? And we can see it again that the number of people hanging up increases the later it is in the day. So that's an example of making chaos, some cosmos or some understanding out of the data chaos. Right, so here we can see that that's where the most people abandon their calls. We can zoom into the tree map on individual calls, right? So here each rectangle represents actually an individual call. And the length of the rectangle represents how long the call lasted, right? And if we see these big red ones, those are also calls, but they're calls that were abandoned, right? So they were long in duration and they were abandoned in the end, right? We also implemented a smooth panning transition, so we can zoom in to get the details, zoom out to get the overview, and then zoom in again on another hour to see the details. Right? And this is a lot of phone calls. Right? So we can't visualize all, say, 200,000 phone calls in just one image. We need some approach that lets us start with an overview of the data, decide where we want to look at more detail, choose that individual hour, and then zoom in on the hour to get the details, right, of the individual calls. Right. On the side, we have a traditional histogram of calls, so that's the volume of calls by hour, right? And we can select different properties of the calls. So, for example, we can filter the calls by wait time. How long did the customer wait in the queue, right, for each call? Or we can focus on just the interactive voice response system. How long did each caller spend navigating through this menu system? Because the longer the customer has to spend choosing different options, the worse it is, right? And the longer the customer has to sit and wait in the queue, the worse the experience is, right? That's an inefficient call center. So we have the traditional histogram. The user can choose an hour, for example, dinner time, and then zoom in on an individual hour, right? So we also can observe that the queue time, the amount of time that customers spend waiting for an agent, for example, increases sharply at 1,300 hours. And these are different options that let the user select, for example, the length of the call, if they want to see all the long calls, right? So these are the long calls, for example. These are all calls that are being highlighted because people waited in the queue for a long time, right? So this is 1,300 hours, so lunchtime. And we can also filter the call by, these are all the inbound calls, for example, to the call center, right? So there are two kinds of calls, inbound calls, but there are also outbound calls. And outbound calls are the calls that agents make to some other agent, for example. So using this visual analytics system, we get an overview of millions of events. We can choose which time we want to get more detail about, zoom in, and then filter the calls by different properties. Right? And this is an individual call. The user can click on an individual call and then get the details about that call. Right? How long they spend in the IVR, how long they spend in the queue, and how long they spend talking to an agent, and how many different agents they spoke to. So I can see here that the user spoke to 2 different agents. But I can also see that they waited in the queue at least 3 times during the call. So that was a complicated call, complicated phone call. Right? So a total of 1 IVR event, 4 queuing events, and 4 agent events. And that was something called a consultation call. Okay. Are there any questions or comments about that example, by the way?
If we can make a simple comparison between we knew about physics, the term chaos, for me that you have, as you explained in the first slide,
Yep.
that we have the real world, okay? We need physics approach, I can see for the composite matter, master equation. Then we follow up in one differential equation or a system of equation. We make a resolution by, thank you, by another something of digital that you use for digital.
Yep.
Then we have a solution, or we can follow in chaos. Chaos for me that there is sensitivity of 2 initial conditions. Please, I don't understand for this case the call, the chaos of the call.
Okay.
The chaos of the data.
The curse of data. Okay. So QPC is the company that develops the software to record the call, the events, right? And all they do is store the events in a database. And they asked us if we could come up with some visualization solutions to help them understand all those events in their database. This is just one solution. This is not the only solution. In fact, we're working on new solutions to this same problem. This is just like the beginning, let's say, of several possible solutions into this problem. It's not the final solution.
Because as I understand, because that system forgot about the memory. If we change the initial condition, we follow for another solution.
Yes.
This is the meaning, simple meaning of the chaos. And I didn't understand this in this case.
That is, what you're describing sounds a lot like the example from the automotive engineering that we have today. So maybe we should talk about that one next, because that's a case where there's a set of initial conditions, there's a set of partial differential equations that describe the fluid flow. We visualize the fluid flow, see what's happening, and then change the initial conditions based on what we're seeing. Yes, so let's look at that example. So that's the engineering example that a lot of people wanted to see anyways. I forgot to mention, if there are other questions or comments, feel free to interrupt me at any time. Yeah. So this is another fun example of the going from data chaos to visualization cosmos. So this is the automotive engine simulation example. Thank you. So this is fun. So these are car components, and these are car components that we find inside the motor. Right? I'm sure everybody here has stopped their car, opened the hood, and looked inside of the engine to try to figure out what was going on. This is a combustion chamber. This is also a combustion chamber. These are 2 examples of combustion chambers. So that's where the petrol or the fuel is injected into the cylinder. It's mixed with oxygen or air. A spark goes off, ignites the fuel, and pushes the piston head down, right? And that's what powers your car. So this is the case of the diesel engine, and this is the case of the gas engine. In the ideal world, the engineers are trying to create a pattern of motion called swirl motion in the diesel engine, in the combustion chamber. It's a helix about an imaginary axis. So here's the imaginary axis, and here's the ideal fluid flow inside the combustion chamber. Now with the ideal fluid motion, it's an optimization problem, and what we're trying to optimize here is the amount of mixing between fuel and oxygen. If we can get this, maximize this mixing, we get the biggest explosion and we draw the most energy out of the fuel possible. And any deviations from that motion reduce the amount of mixing. And this is the case for the gas engine. In this case, we're trying to achieve a tumble pattern of motion, which is also a spiraling pattern about an imaginary axis that points straight out of the view plane. And this is easier to achieve, by the way, and this is less easy. And there's an analog solution to this problem, right? And that's to build an engine, inject it with fuel, and watch the fuel explode. And that's expensive though. It's expensive to build those cars, and it's even more expensive. By the way, there are also experimental engineers, automotive engineers, that try to build glass-type engines that you can actually observe this mixing process in the real world, but that's expensive. So the engineers turn to computational fluid dynamics as a digital solution to these problems, to study the mixing of fuel with oxygen inside a combustion chamber. Does anybody here do CFD simulation? Probably there are a few engineers in the neighborhood that study this problem. So the digital solution is from computational fluid dynamics, and computational fluid dynamics computes the flow through the engine. Right? It tries to predict how the flow is going to move through the engine, right? Using engineering. But those CFD simulations cause another problem. And the problem is that they're very, very big, those CFD simulations. Right? They're usually several gigabytes in size, or terabytes even. So let's look at that example. So this is what studying the fluid flow through these combustion chambers looks like. We're using data visualization. So that's the fluid as it's being injected into the cylinder. And this is the piston head. We don't see the piston head, but the piston head defines the bottom of the geometry. Right? And as the particles are released into the flow, we can start to get an idea of this kind of tumble motion that we're looking for. Right? We can start to see the tumble motion. It's very far from the idealized version of the tumble motion that the engineers are trying to achieve. So this is an example from flow visualization. So these green tubes represent vortex core lines. Those are the axes of rotation. So there's a flow moving around the vortex core lines through inside the volume. This is what it looks like when we try to visualize the flow at the boundary. So these are so-called critical points. They're like sources and sinks in the flow, right? And these are special kinds of streamlines that are called the separatrices. They separate the flow into different regions of behavior. This is what it looks like when we look at the swirling flow inside the volume using volume visualization. Those regions are different areas of swirling flow. So this is the time-dependent behavior of the flow, or the flow topology, right? These are our vortex core lines, so we have flow moving around the vortex core lines, and these are called critical points. So those are points like sinks in the flow, sources of flow, and also what are called saddles, flow saddles. Right, there's a saddle as it moves across the geometry, and you can see that the fluid patterns are quite deviant from that ideal tumble motion and swirl motion that we saw in the diagrams. This is a volume visualization of the flow. So these are different regions of swirling flow, and one is rotating in the clockwise direction, and the other one is rotating in the anti-clockwise direction. Right? And that's what they look like over time. It's pretty complicated to observe, by the way, as you can see. And these are the same data set, but two very different styles of visualization. One is using a feature-based visualization that extracts the features of the flow, and this is called a texture-based visualization that tries to visualize all aspects of the flow at the same time. This is visualizing special different features inside the flow. And that's what it looks like to try to visualize computational fluid dynamics data. Do we have time for one more example?
Yeah, 10 minutes.
10 minutes? Okay, let's look at one more example. I forgot which one it was. Which example we wanted to look at. Was it the geography and the healthcare one? Yeah. Healthcare, okay. Because everybody wants to figure out how to lead a healthy life, right? What were you guys going to say back there? Yes. I would like to comment that that's a very good question. So she asked about fuzzy numbers. What if in the visualization community, we call this uncertainty, or uncertainty visualization. So all the numbers of the universe have some uncertainty, right? And I don't have a special example prepared here right now with visualization of uncertainty. We have done some work on visualization of uncertainty, and it is a very active area of research, and it's a very important area. But I didn't bring an example with me today. I could just say that we call it uncertainty visualization. We have done research on the topic, and there's a group of people very actively involved. And I will add one more thing. It's a neglected area of research. So I think it's more important than the attention that it's currently getting, let's say. And I'm not the only one with this opinion. A lot of people think that uncertainty visualization is a little bit neglected.
So are you including the fuzzy numbers and fuzzy behavior in your data model?
Yes, we are. And in fact, you may have noticed probably the inspiration behind your question. Hold on. You probably noticed that there are different styles of visualization in this example. So in this style, all of the fluid flow, there is some uncertainty in the fluid flow because the way that the fluid is being depicted, it's not in a binary fashion. It's got some fuzziness in it, right? It's semi-transparent. And those massless fluid particles have a volume, right? The boundary of the volume is not sharp. In this example, this is a discrete representation of the flow. These vortex tubes, that does not include any fuzziness, right, in this style. Right? It's very discrete. It's either on or off. Right? It's either part of the vortex core line or not part of the vortex core line. But we'll see some examples of fuzzy numbers. So this style of visualization, this gray texture, is showing the orientation of the flow, but not exactly. We don't know, we can't make exact conclusions about the flow. We could call it something like a fuzzy fluid flow. And this is also not a binary representation here. This is a volume, but it's a fuzzy volume. And it indicates a region of fluid flow that is rotating with a certain amount of velocity. But it's not binary, it's not on or off, it's a smooth transition from 0 to some measurable number. So it's like a fuzzy visualization. This one again is discrete, so there's no fuzziness. But in the previous volume visualization, it was fuzzy. Any other great questions about that? So we'll look at the healthcare example before we wrap up. So, geography and healthcare. This is a fun one. Right? This is a really fun one. They're all fun, right? They're all exciting. They're all very challenging. So in the United Kingdom, which is currently where I live, that's why I keep mentioning it. There's something called a national healthcare system that tries to provide a basic amount of healthcare for everybody living in the UK. So it's a great objective, ambitious and objective. And it's called NHS, or the National Healthcare System. And the goal is to understand public health, right? What is causing people to die, for example, prematurely? Or what are the current most prevalent healthcare diagnoses? What are the kind of illnesses that people get the most often, for example? And if we knew that, we might be able to make some changes. Now, the analog solution to this problem is just to hire more staff to study the problem, right? And in the ideal world, we could hire staff that would actually go around and give everybody a health test and then measure directly the health of the public. That would be very expensive, but it's theoretically possible in the real world. The digital approach is to collect the health diagnoses in a database. So every time you visit a doctor in the United Kingdom, if you are diagnosed with some sort of health disorder, let's say, or less than optimal health, that data is stored in a database. Right? And all the data is grouped into regions called clinical commissioning groups, or CCGs, which are regions in the UK. And this is what the regions look like. Right? So everybody belongs to a CCG. And there's an organization called Public Health England that collects all the data and then releases it to the public. Right? It's on a website called National General Practice Profiles. That's a picture of the website where they're uploading it. And they're hoping that somebody can visualize the data and help them understand it. And this is the kind of standard visualization that they're using, which is a scatter plot. But the problem with that is we don't know anything about if maybe there's a coronary heart disease being depicted there. Well, if I asked you where in the UK are people getting the most or suffering the most from coronary heart disease, you might not have any idea because the data is not coupled to the geography in any way. right? It's just a scatter plot, which is still useful, but it could be even better. So this is the geography. These are the CCGs. And there are many different kinds of illnesses and diagnoses, right? There are hundreds of them. So how do you visualize or couple this multivariate data, these different diagnoses, together with the geography? Is it possible even? This is one approach. It's called a cartogram. Has anybody here ever heard of a cartogram before? It's where you take a traditional map and then you distort each region in the map according to some variable. Probably you've all seen it before. If you've ever seen a world map where the size of the countries is distorted by the population, you see like China exploding, India exploding, and then all the other countries getting smaller, right? Because the land mass shows the population of the countries. Well, this is a so-called cartogram, where the land has been divided up into equal units of area. And then we can visualize different diagnoses. But if we have, say, 10 different diagnoses, it's difficult to see what's happening, right? For example, in this region, I can't see what's happening underneath the surface due to occlusion. So the question is, can we somehow modify the cartogram so we get the information about the geography and the different diagnoses at the same time? That's the question. And that's our last example.
So let's look at that.
And we tried a visualization that tries to combine tree maps, which we saw in the first example, with traditional maps, right? And this is what it can look like. So again, this is from the UK. And what we're seeing, these are the CCGs. These are the 209 different regions that everybody's divided up into in the UK. That's what each one of these boxes represents. And they're in the approximate location on a map that they would be on the map, but with some error, right? So and this is what the layout algorithm looks like. So we start with very small regions and then we expand them so that they fill up the screen space by some metric, right? The more screen space they fill up, the easier it is to see the data inside each CCG, but the more the map is distorted. So we let the user make a trade-off between the amount of distortion and the amount of screen space that they use to visualize the data. So it looks kind of complicated, right? So let's just quickly look at that example again. So that looks pretty complicated, doesn't it? These are different diagnoses: coronary heart disease, heart failure, stroke, chronic kidney disease, diabetes, hypertension, coronary, I can't remember that one, mental health disorders, osteoporosis, arthritis, cancer, epilepsy, and so on. Sounds like fun. But, okay, we have this complicated map, but we can already make some observations immediately. Even though it's complicated, showing lots of data. For example, we can see right away that hypertension is the most common diagnosis in the UK. We can see it right away from all these very large yellow rectangles. So each diagnosis is mapped to a rectangle with a color. And I can see lots of big yellow rectangles, and those stand for hypertension in this case. That also means high blood pressure. So the UK diagnoses a lot of high blood pressure, and we can see number 2 right away too, which is diabetes. Diabetes is that magenta rectangle that keeps appearing. It's the second largest diagnosis that's occurring all throughout the UK. Doesn't really matter where we look. So right away we can start making observations about some of the healthcare and some of the health disorders in the UK by combining this multivariate data with the geography. And this is what it looks like if we map the size of the rectangles to the population size that they represent, right? London's here, by the way. So London has the most dense population, and we would expect that the biggest rectangles would be in London, but actually the biggest rectangles are out in Cornwall. And in fact, that's the area that gets less money, right? So a smaller number of doctors have to serve a larger population in Cornwall than in London, right? This is what it looks like when we try to collect some of the clinical commissioning groups together in a hierarchy, right? And then we can click on any node in the hierarchy and get more details. So this is a single CCG, and we can find out the numbers of diagnoses in each category for a single CCG in a zoomed in or a close-up view. We have lots of different user options about how to study. So this is slowing down the node layout process, what we call the node layout process. Right? And that's if we want to visualize the amount of distortion. So how far away does a CCG traverse from its original location on the map to its new location on the cartographic tree map? So this is letting the CCG regions change their size. So some of them are small and some of them are big. Now, somebody asked about fuzzy numbers. So here's an example where we visualize some error. So this is visualizing the amount of the distortion that the layout algorithm makes, right? So whenever the neighbor relationship between two CCGs changes, a line, an edge is drawn, right? Because that represents some distortion. And these are just some different rendering options that let us focus in on some specific areas rather than trying to visualize all the data at the same time, right? Because it is very complicated to visualize everything at the same time, right? These are different color maps, so we can use different color maps. That's adding a gradient to the colors, so a little bit of shading to the colors. So focus and context visualization. This is showing all of the above average diagnoses for it. So we have this user option that says, show me all of the diagnoses in the regions that are above average. Right? So turning off the below average and showing only the above average. Right? So we can see, for example, this region has all of the rectangles showing now are above average in their prevalence. So we have above average hypertension, for example. And then we notice right here a region that's lacking, right? That means the health diagnoses are below average. Anybody know what that area corresponds to? Any guesses? Anybody been to the UK before? Who's been to the UK? Somebody here has been to the UK. That's amazing. I've never been in an audience before where nobody's been to the UK. Okay, you're forgiven for not knowing the answer to that question.
I guess it's London, no?
Yes, it's London. That's right. Very good. But you've not been to the UK. You have been. Okay, good. So this is London. So we can see, oh wow, London is healthier actually than the other regions, which is a big surprise, except not always. London's not always healthier. Right? We can see some of the areas in the north that are very unhealthy. Right? This is the below average filter. Right? So we can see some regions in the north that are unhealthy actually because they're above average on all indicators except for one or two. And that's just focusing on individual variants. So we can click on individual variants in the color map and just focus on those. We don't have to choose them all at the same time.
I guess we still have 5 minutes with the questions.
Okay, that sounds like a good idea. So, why don't we pause there? Are there any questions from the audience?
For empty zone, it doesn't say highly person. We can have a classification about lack of information for empty zones. It doesn't mean necessarily a healthy person. We can not have information about this zone. So interpretation and semantics about zones, we have two categories. So we have
Yes.
different interpretation in the past.
You are correct. So this is definitely not a perfect data collection process by any means. What's missing here? Well, some things are missing, like the people that don't like to go to doctors. Like who here doesn't like to go to doctors? I hate going to So I won't always go to a doctor if I'm about to die. If I have some health disorder. So that data is missing. Another thing that's missing is perhaps private service or private health care. Right? So a lot of people will go to a private health care service instead of a public health care service when they're diagnosed with something. For example, like I couldn't find a public dentist, so I had to hire a private dentist. And that's something that wouldn't be recorded in this data.